Hi YouTube, time for another installment on the video series about the Bren-Tronics vehicle mounted battery charger, or VMC. This is one of the battery adapter units that comes out of that battery charger. In short, it takes a standardized spade type connector on the bottom and provides access or some sort of interface with the various different types of batteries that like the US military and I guess Bren-Tronics standardized on. They're relatively simple. There's one screw, two pull handles to allow you to lift it out, and they fit, amongst others, the BB-8590 batteries with access to the charge enable pin. That's the charge pin. That's the center pin that you would otherwise have to connect to, but it does not give you access to the state of charge, the SM bus pins on this. So I think this is a dumb adapter, but somehow this adapter manages to communicate with the charger to tell it what is installed and what voltage to apply. My theory is there's either an EEPROM in here or it's analog and it just has a series of resistors to configure charge, voltage, and current. So time to dive into this. On the outside we've got very idiot-proof hinge side label to say install this way up, which actually I guess isn't so much idiot-proof as being very certain, because it's symmetrical other than this slightly offset mounting screw. And the charger is designed to be mounted, I don't know if it's designed to be mounted upside down or just horizontal, but either way, they put labels up and down so that you can access the charger no matter what. Alrighty, let's unscrew some screws. I'm gonna lay the screws out in the orientation which they came out. It's amazing what you can get surplus on eBay. Oh no, it's just difficult to get at. Alright, so bottom plate looks like it's fairly standard, probably ABS. There's no markings other than a part number and a revision. What do we have in here? We've got, okay, so I don't think I can really disassemble this at all, other than physically examining this. I'd have to be pretty destructive when disassembling this. Okay, so I've done the hard part of desoldering all of these connections. So now we're just left with the main board on the battery adapter. So it's interesting to see that they basically bridge with individual wires to the breakout boards and everything's soldered. It makes sense because this is a high vibration environment and you want a lot of compliance and flexibility if anything shakes. You know, if you put a connector here, it'd be harder to stay on. So I'm going to disconnect and desolder these various points, and we'll go from there. Alright, so all the wires are disconnected and clear. I've got a photo of how this thing went together beforehand. So let's dive deeper. Alright, I think I have it all desoldered finally. I needed to buy extra solder wick because I ran out, so I ended up just buying the 50-foot spool, and that'll last me another couple of years. I had to use a not insignificant amount of wherever it went. Where did it go? Oh, it's right here. Chip Quick. It's a super low melting temperature solder alloy. So you apply it, it alloys with the existing solder and reduces the melting point. which allows you to remove it more easily without melting or damaging other components. Alright, so I've managed to desolder both of these as well as all of the pogo pins, or the spring-loaded connector pins, on this battery adapter board. And what I found is quite interesting. My original hypothesis was that these relays would select between the different batteries present and that there were only 2 charge channels on this board. In fact, it's quite the opposite. What it appears to have is 8 channels of charging through all 4 of these headers. However, only the BB-8590 style batteries have relays, which are double pole single throw relays. And these relays just connect up the 2 different sides of the batteries. Nothing more than that. For the other batteries, like battery 7, battery 5, batteries 4 and 6, and battery 3, all of those batteries have a direct connection to the board. So I'm going to go pull up the schematic now, and admittedly it's a little messy, but here we go. Alright, so here's what we have on the schematic. We've got all 4 headers, as well as the breakout boards here, just so I can trace where on the actual unit it connects to, which of the mating pins to this connector. But regardless, here we go. So, batteries 1 and 2 are identical copies. They have SM bus clock for batteries 1 and battery pin 1 through 4, or battery pin 1 and 4, common for both SM bus connectors. So both of the 2 SM bus headers share the same clock for pins 1, 4 and pins 2, 5. Same down here, but the data are broken out into 4 separate pins. Charge enable is actually the center connector on here, as well as the center connector here. And you apply 5 volts or so between charge enable and the center header pin here. Regardless, both batteries 1 and 2 have identical, what appear to be shunt-based voltage regulators. So presumably this this signal here is something like 24 or 27 volts, and it applies voltage limited by this 0.9 kilo ohm resistor, and then this shunt ends up setting what the voltage is. It's interesting because normally this resistor would be a little bit lower, but it almost looks like there's 2 regulators in series, and I think it's a feedback pin. So this goes to the charge enable pin and applies what appears to be 10 volts, which is really confusing because if you measure from the center pin here over to this pin, it's something like 10 volts, and then from this pin to the other side pins, it's something like 6 volts. So it's kind of misleading what the true voltage is between those 2 pins. Reference to ground. Anyway, so you have another shunt here with a 1K and another shunt regulator, and then a very low resistance 100 ohm that goes straight back to this connector here. And I think it's some sort of a feedback to detect when there is a load on this charge enable pin, because normally the charge enable pin would float high until the battery's plugged in, and then this charge enable voltage droops a little bit as the battery draws a little bit of current through this pin, which then drops this voltage out and signals the charger, hey, a battery has been plugged in here. Other than that, in the relay sections that are identical to each, you have 2 relays, 2 freewheeling diodes, and both double pole single throw contacts on each relay are paralleled. Nothing special over here. So that's battery 1, and that's battery 2. Battery 3 is a bit of a weird one, where battery 3 has just a charge and a ground terminal, and these go to here. And it's interesting because you have the what's the best way to put it? You have on the header, well, it's easier if I just pull this up as an example. So this header is here. I'll flip it over so you can see the mirror image of it. So certain pins like BAT3 charge are actually paralleled between both of these two pins. Other pins like this BAT3 charge up here, which would be this pin over here, are actually not parallel together. It's a little hard to see, but there is no bridging trace between those two pins. It's just interesting because you can see here the heavy trace goes to the terminal, and then you have a thin trace that goes back up over to here. So what does that tell us? It tells us that you have voltage monitoring. It's almost like a Kelvin connection. If you're familiar with 4-wire resistance measurement, you would have a high impedance trace, in which case, in this case, this BAT3 charge, as well as the low impedance trace, this trace here, both going to that terminal. This is the one that supplies the voltage, this is the one that measures the voltage. So instead of just, I guess, applying voltage and trying to measure through the same contact back inside the charger mechanism, it does it separate. It also means that you can cut power to this pin and still measure voltage over here. So that's battery 3. Battery 4 shares a common contact. That's the best way it's possible to show it here. Yeah, let's refocus real quick. Can I actually focus to that? Yeah, I can. So you can actually see here E402, these terminals. This is just a mirror, so this is the center, this is the outer, and that's the furthest most outer. So this pin and this pin are parallel, these two are parallel, and this is on its own. So what you have is a voltage, a charge enable, and a ground. A lot of these batteries have a charge enable input, and it won't accept current until you actually apply a voltage to that extra terminal. In this case, you have two charge terminals and a enable pin as well. And the interesting thing is that with the arrangement here, you can plug a battery in over here or plug a battery in over here, but plugging in either excludes the other. And that's why on the schematic, you have all of these kind of sharing a similar footprint in terms of sharing a ground and sharing other terminals. Okay, so that's batteries 3, 4, and 6 taken care of. Battery 5 is off in the corner here, and it just has 3 terminals. It has a center, and it has the common outer pins, and that's just it. It applies a voltage, and it accepts charging current. That's it. So that was battery 6. Battery 5. Battery 7, similar here. I'm not sure what this other pin is. There's a charge and a common, and then there's this other terminal here, which appears to be some kind of a either a balance, like a intermediate sense lead. It just leads back to one of the connectors. I'm trying to remember where it went. As you can see, this header adapter is quite busy. I think it's somewhere in this neighborhood. Yeah, there's BAT7 charge, there's BAT7 bow. So another common theme here is these two headers are high current, these two headers are sensing and low current. And you can start to see some commonalities if you flip these around. Certain pins are parallel together, certain pins are for SM bus, certain pins are voltage sensing, and they're not implemented on this side, whereas they may be implemented here. So I'm sure there is some underlying standard behind this, but it's a little bit difficult to discern what exactly it is. The other question we have to ask ourselves is, how does the charger understand what battery adapter is plugged into it? And there's only 3 things that seem to indicate that. This resistor here, this resistor here, and what is an unpopulated either resistor, well, it looks like it's a resistor, not a jumper, because it's signified by component R3. So you have 2 resistors, you have a 2.75 k ohm and a 4.62 k ohm. Not sure exactly what these are intended to set, and you'd actually have to start to decompile firmware and figure out what voltages it's expecting. So there's a huge, probably a table somewhere in the design documents for this charger that would say, if you see a certain voltage on this pin and a certain voltage on this pin, and these 2 resistors comprise, you know, half of a voltage divider, you would see a certain voltage, which then implies you have a certain type of adapter plugged into it. I would need to look at more of these battery adapters to really reverse engineer it. So I think in the sense of co-opting this battery adapter to charge other types of batteries, it's going to be a lot more difficult than I thought. The best I might be able to do is float charge, to float charge a lithium battery just using one of these isolated outputs. And then it's a question of, will the charger just accept that I'm applying a current drain there when it's going to expect to sense a voltage, a particular voltage on each one of these pins. I can't just apply a load to some of these terminals and expect it to be okay, because it's also expecting to see feedback from these 3 pins, 2 of which I really don't know what they do. It's expecting, it doesn't actually have SM bus header pogo pins populated on the adapter unit, so the SM bus really isn't even connected or implemented, strangely enough. And you really have this other enable voltage shunt, so you get a certain voltage in, and this goes, I guess, to ground or something, and then you have a certain voltage applied to here, but it's also sensed over here, and it's doubled up too, which is a little strange. So oh no, that's bat enable VN, so that's where all of the voltage regulator blocks down here, over here, and here get their power from, their voltage. So that would be where the sync is, I guess. Yeah. Other than that, I'm honestly not sure I can do that good a job reverse engineering this without actually plugging it in situ and taking more measurements, but at the very least I have a very preliminary look under the hood, and I initially thought that it would be easy to repurpose, but apparently not so much. For the time being, I think the best I can do is, you know, reassemble this and use it as is, and attempt to tap either battery 3 on these two header pins here, or battery 5, possibly battery 7. Those 3 positions seem to be relatively simple. They may charge relatively slow though, and that's the other thing as well. What I suspect is happening is the 2 or 3 configuration resistors, at least what I'm proposing is the configuration resistors, these resistors instruct the charger to go to its lookup table and say, okay, I have this particular type of charging adapter loaded, which means set all of my outputs to certain values. So I can't arbitrarily assign them without decompiling and recompiling the firmware. with my own custom values. Unfortunately, I think this is relatively limited unless you can do something with the specific voltages here. But I mean, it would be great to be able to use this to charge power tool batteries or other things in situ. We'll see. I'm going to have to experiment some more. So I think that's it for this video, and I'm just going to wrap up with reassembling that adapter unit. So until next time.